Welcome back, learning enthusiasts. Uh, in this video, I want to go over the solutions to section 1.1, 1.2 in John Stillwell's book, Mathematics and Its History. If you haven't seen video on the chapter summary for section 1.2 and 1.1 and 1.2, that's already posted on the channel. You could take a look at that. I actually think you should watch that before you watch the solutions here, and also try these problems before you actually look at my solutions. I always say that as a warning in the beginning of these videos. You'll get more out of the problems if you actually try them yourself first before looking at the solutions. But anyway, we'll go over the solutions for section 1.1, 1.2 in this video. So let me bring up my solutions first. Let me just say something about the format here that I have the solutions in. I actually wrote up solutions for chapter 1, the entire chapter 1 in this book a long time ago, which is why they're written out here in you can see them here written out in Word, in a Word file. So I have these all written out nicely in Word documents for chapter 1, but just be aware that once I get to chapter 2, I don't have any more nicely written up solutions like this. So we'll have to go back to my handwritten solutions for chapter 2 and onward. But for now, we have this nice document to look at. So here we go. So question number 1 lists the integer pairs a comma c in Plimpton 322, which we talked about in the chapter itself. So a is the numbers a are in the first column, the numbers c are in the second column, and just to refresh your memory, on this tablet, this clay tablet, these are purporting to give solutions to the Pythagorean theorem. In other words, a squared plus b squared is equal to c squared. Notice that we have the a's listed and the c's listed. What is missing is the values for b, which is what he wants us to explore in this the next couple problems. So let's actually look at that. Okay, question 1 in section 1.2 says, for each pair AC in the table, compute c squared minus a squared and confirm that it is a perfect square b squared. And he wants us to notice, once we do that, that in most cases, the number b is a rounder number than a or c. What he means by a rounder number is so a round number is one that's divisible by a lot of factors. In particular, you want it to, a round number, the more that a number is divisible by the base that you use, the rounder it's considered, because the more zeros it has at the end in the numeric representation. So here, the Babylonians actually counted in base 60. So what he means by, in quotes, round, is he wants you to show that a lot of these numbers are divisible by factors of either 60 or 30 or 12, things like that. So that's what I did here. So in order to calculate b, you would take c squared minus a squared. So I'm just doing that for all the numbers here in the Plimpton tablet. All right, so for example, for the first pair of numbers, 169 squared minus 119 squared is 144, 14,400, which, if you notice, is a perfect square. It's 120 squared. And notice that 120 is a rounder number than 169. I'm sorry, rounder than 13 or 17. 119. So was it 169? Yeah, 169. Sorry, it should have been one. Sorry. This number and this number is less round than that number. So 120 is rounder in the Babylonian system than 169 and 119. 169 is 13 squared. 119 is 7 times 17, right? Whereas 120 is 2 cubed times 3 times 5. Notice it's divisible by 60. So that's what he means by rounder. And I won't go through all of these because they're just calculations. So you just use the numbers and just show what he wants you to show. But if you look, you can see I actually did all of these. numbers and showed what he wanted to show. Like I said, I won't go through all the details. You can do it yourself. It's just numerical calculations. That's question 1. Right. Question 2 says show that most of the numbers B are divisible by 60 and that the rest are divisible by 30 or 12. And again, it's just a calculation thing. So I just did that here. And if you look, all of the numbers that you get for B, the value of B, are either divisible by 60, 12, or 30, which again means that they're rounder, rounder than the other numbers in the Plimpton tablet. And okay, so why do we care about that? Well, if you remember back to, he has a note here after the question, which I'll read in a second, but the point is, we think that the Babylonians created this list of numbers by using the formula that we went over in the section itself in the summary. The reason we think that is because these values B seem like easy numbers to calculate with in base 60 because they're round. So it seems like the way that the scribes or whatever who constructed this tablet of numbers, they chose the number B, right? They chose an easy number to calculate. And then from the value of B and the formula that we looked at, they calculated the other two numbers, if that makes sense. That's why they think that this tablet was created possibly using a formula like, the one that Pythagoras developed or whatever, or maybe Plato, or obviously these were before those people, but this tablet was, I think they said, dated around like 1800 BCE or something, and Pythagoras was 500 BCE. So, well before Pythagoras and Plato and Euclid. But that's why they think that, because the numbers B look like they were easy numbers that were chosen by the scribes because they had to calculate the other two numbers. So they think that this is evidence that the Babylonians, even all the way back then in like almost 2000 BCE, had at least some semblance of a formula for getting Pythagorean triples. So that's really interesting to me that we have that evidence and that we can, figure that out, how they did this all the way back then. Let me just read his note here that he has after question 2. He says, such numbers were in fact exceptionally round for the Babylonians because 60 was the base for their system of numerals. It looks like they computed Pythagorean triples starting with the round numbers B, and that the column of B values later broke off the tablet. Euclid's formula for Pythagorean triples comes out of his theory of divisibility, which we shall take up in section 3.3. Divisibility is also involved in some basic properties of Pythagorean triples, such as their evenness or oddness. And we'll look a little bit about the division properties of Pythagorean triples in the next couple questions. All right, so that's question 2. All right, question 3 says, show that any integer square leaves a remainder 0 or 4 upon division by 4. Right, so we just go through the cases. So there's only 4 types of numbers we have to consider because there's only 4 remainders that you can get when you divide by 4. You can get a remainder 0, a remainder 1, a remainder 2, or a remainder 3. So, we'll just go through those 4 cases. So case 1, let's say n is divisible by 4. That means that n is of the form 4k, and if you square it, you still get a number that's divisible by 4. So the remainder is 0, right? So it's congruent to 0 mod 4 if you want to think about it like that. Right, the next case is if the remainder is 1. So n is 4k plus 1. If you take the square, and you simplify everything, you get a number of the form of 4 times 4k squared plus 2k plus 1. Notice that 4k squared plus 2k is another integer, meaning that n squared in this case is congruent to 1 mod 4. Okay, case 3, we'll take a remainder of 2. So n is of the form 4k plus 2. And if you square that, you get a number that is congruent to 0 mod 4 if you simplify. Right, and then if you take n congruent to 3 mod 4, in other words, the remainder is 3, then n has the form 4k plus 3, and if you square it, you get a number, the square that is a number that's congruent to 1 mod 4. So when you square a a number, an integer, it'll either be the square will either be congruent to 0 mod 4, meaning when you divide by 4, it'll have a remainder 0, or it'll be congruent to 1 mod 4, meaning when you divide the square by 4, you get a remainder of 1. Okay, that'll be important for the next question. So that's the answer for question 3. Question 4 says, deduce from exercise 1.2.3 that if ABC is a Pythagorean triple, then A and B cannot both be odd. Okay, so this follows directly from the previous question. So if A and B are odd, that means that A and B have to be either of the form 4k plus 1 or 4k plus 3. And in both of those cases, when you square the number, remember you get a number that's congruent to 1 mod 4, which means that when you take A squared plus B squared, you'll get a number that's congruent to 2 mod 4 if in either of those cases, right? That's if they're both A and B are both odd, and obviously that can't happen. Their sum will be congruent to 2 mod 4, which is impossible since C squared must be congruent to 0, 1 mod 4 by the previous exercise. Like I said, it follows directly from that. And that's it. Those are the 4 questions for section 1.1, 1.2. So let me just stop the screen share here for a second. We'll continue with section 1 as we go along. The next video though will be section I think it's section 2.2 in Taylor. I have to finish up chapter 2 in that book next, so we'll do 2.2, and that'll be we'll do the chapter summary and the exercises for that next, and then we'll I'm just going to add this basically into our cycle of books. There is one more thing I want to add to our cycle also, which is I want to go through an elementary book on cryptography as well. When I decide which one I'm going to do, obviously I'll post a video about it and stuff. So again, thank you guys for watching. Let me know what you think in the comments, and do like and subscribe if you enjoy this content, and I'll see you guys in the next video. Until that time, keep learning.